Welcome to the video for Chapter 10. In this video, we're going to learn about correlation and regression. Correlation and regression are two statistical analyses that we can do with paired data. Paired data is when each person in the sample gives us two different values. So for example, height and weight. If we had people from a sample, we could measure each person's height and weight. So each person would give us two different values. That would be an example of paired data. Here's another example of paired data. So in this particular study, we took several people and we asked them how many hours they spent studying and preparing for the final exam, and then we looked at their final exam grade. So 6 people were a part of this research. Person A studied 6 hours and had a final exam grade of 82. Person B studied 2 hours, had a final exam grade of 63. Person C studied 1 hour, had a final exam grade of 57, and you can see the values for the others. Now, the question that we want to try to answer whenever we have paired data is this: does a linear relationship exist between these two variables? Now, to help us answer that question, one of the things that we could do is we can make what's called a scatter plot. So a scatter plot is a graph that we can make when we have paired data. All that you do is you mark the horizontal axis with the values of x, mark the vertical axis with the values of y. Notice I cut part of the y-axis out between 0 and 50 since we didn't have any values in that range. But then for each person, you would just mark their location on the graph. So, for example, if we go back to our data, person A studied 6 hours and had a final exam grade of 82. So, study for 6 hours, so go over to 6, final exam grade of 82, go up to 82, and you can mark their dot. Okay, we'll do one more person here. So, person B studied 2 hours, had a score of 63. So, on the scatter plot, we would go over to 2 and go up to 63, and we would put our dot. And we would do that for each person in the study. And so once we've got everybody's dots on the graph, we have what's called a scatter plot. And the question, like I said, that we're trying to answer is, does a linear relationship exist between these two variables? Well, relationship means pattern. Linear means straight line. So what we're really asking here is, does a straight line pattern exist between these two variables? And you might be able to see that in the scatter plot. Okay, now a straight line pattern doesn't mean that the dots have to fall into a perfectly straight line, but it means that a straight line should more or less, generally speaking, capture the pattern here. So I don't know, perhaps there's a straight line like this that could capture the pattern that's in these dots. It's debatable whether that line captures the pattern. Maybe it does, maybe it doesn't. Maybe the pattern that we have here is more of a curved line pattern. Okay, so that's where the debate can come in. So what we're really looking for is, like I said, does the scatter plot show a straight line pattern? That would be a linear relationship. Now, some straight line patterns are called positive linear relationships because a straight line captures the pattern and that straight line slopes up. Other straight line patterns are called negative linear relationships because a straight line captures the pattern, but the line slopes down. But then you have some curved line patterns. These are called nonlinear, not a straight line or curvilinear. And then you have some scatter plots, some paired data where there's no relationship. In that last picture, you can see dots are just kind of everywhere with no rhyme or reason. So in this class, we're just going to be looking for the linear relationships. And we'll either say, yes, there appears to be a linear relationship here, or no, there does not. If we say no, there does not, that may mean that there's a nonlinear relationship, or it may mean that there's no relationship at all. Okay, but we're really putting a dividing line right here and saying, okay, do we have a linear relationship or not? Now, looking at the scatter plot, like I said, is rather subjective. Okay, we could all have our opinions about whether or not a straight line pattern exists when we look at some dots in a scatter plot. A more objective way to come to some conclusion is to do what's called a correlation analysis. Now, a correlation analysis will be a statistical analysis that we can use to determine if a linear relationship appears to exist between two variables. Now, in order to do a correlation analysis, the data must be quantitative and obtained from a random sample. The scatter plot has to at least suggest that a linear relationship is a possibility. In the two sets of data, there should be no outliers. And the two variables, which we call X and Y, should come from normally distributed populations. If you don't meet all of these conditions, then you really can't get valid results from your correlation analysis. Now, a correlation analysis is based on what we call a correlation coefficient. For samples, that's represented by the letter R. And for populations, the correlation coefficient is represented by the Greek letter rho. It looks like our letter P, but that's the Greek letter rho. It's the equivalent of the letter R in the Greek alphabet, and that's the correlation coefficient for a population. Now, the correlation coefficient is always going to be a number between -1 and +1, and it measures the strength of a linear relationship between two variables. So if you think of a number line that goes from -1 to +1, if you have a correlation coefficient that is close to -1, that's going to say that there's strong evidence for a negative linear relationship. A correlation coefficient that's close to +1 would mean that there's strong evidence for a positive linear relationship. When the correlation is in the middle, close to 0, that is weak evidence for a linear relationship. So our conclusion in those cases would be that no linear relationship appears to exist. Okay? In order to say that a linear relationship appears to exist, we want to see strong evidence. Okay? Our assumption is that there is no linear relationship. In order to say that's a bad assumption, we want to see strong evidence against it. It's like innocent until proven guilty. You need strong evidence, okay, evidence beyond a reasonable doubt before you declare somebody guilty. Well, same thing here. We assume that there's no relationship, no linear relationship, and only if we see strong evidence against that will we reject that assumption and say that a linear relationship appears to exist. Now, here's the formula to calculate a correlation coefficient for a sample. It's a big formula. There's a lot to it, but I'll work through an example with you, and I think you'll see it's not quite so bad. Okay, just notice that you've got n, which is the sample size that shows up in a few places, and then you have a lot of different summations. The summation of all the x values, the summation of all the y values. This would be the summation of x times y. This is the summation of x squared. This is the summation of y squared. Okay, now if you have the summation of x in the parentheses with the square outside, that means you add up all the x values first and square the total. When you have the summation of x squared where the square is inside the parentheses, that means you square each value of x first and then add them up. Okay, and typically we'll round this to 3 decimal places. So in order to do this calculation, I like to make a chart like this where I've got all of my people listed in one column. So they're just labeled A, B, C, D, E, and F. That's 6 people, so our sample size is 6. I list all of the values for the first variable, which in this case was the hours that they studied for their exam. And then in the second column, or third column, I guess, you would have the values for the other variable, which in this case was the final exam score. Okay, so hours of study is labeled X, final exam score is labeled Y. So I can add those columns up. I get my total for X is 19, my total for Y is 433. Now I'm going to create 3 additional columns here. The first one is X times Y. And what I do in this column is I take each value of X times the corresponding value of Y. So 6 times 82 is 492. 2 times 63 is 126. 1 times 57 is 57. 5 times 88 is 440. And I would just continue to do that all the way down the line. Once I have that column filled in, I can add it up. In this case, it's 1476. Then I create a column for X squared. So I take each value of X and square it. So 6 squared is 36. 2 squared is 4. 1 squared is 1. 5 squared is 25, and so on. add up that column, the total for x squared is 79. And then do the same thing and create a column for y squared. So take 82 squared, you get 6724. 63 squared is 3969. 57 squared is 3249, and so on. You can add that column up and get your total 31,935. Now we plug the values into the correlation coefficient formula. So that formula started off with n, which is the sample size, 6. Then it was the total of the xy column, so that's the 1476. And then we had minus the total of x, which is 19, times the total of y, which is 433. That's the numerator. Then big square root covers the entire denominator. There's two sets of brackets. In the first set of bracket was n, which is 6, times the summation of the x squared column, which is the 79, minus the summation of the x column, which is 19, and that total is squared. Second set of brackets, same sort of thing, but just with the y values, sample size 6. The summation of the y squared column, that's the 31,935, minus the summation of y, which is 433, and that total squared. Now to simplify this, just take care of all the multiplications first. 6 times 1476 is 8856. And then 19 times 433 is 8227. 6 times 79 is 474. 19 squared is 361. 6 times the 31,935 gives you 191,610. 433 squared is 187,489. Now do the three subtractions. So 8856 minus 8227 is 629. 474 minus 361 is 113. 191,610 minus 187,489 gives you the 4121. Now at this point, I would suggest that you either highlight or mark this step in some kind of way, because you will want to refer back to it a little bit later, as you'll see. But anyways, to continue the simplification process here, we have multiplying the 113 times the 4121 gives us this 465,673. So take 629 divided by the square root of that 465,673, and you get 0.922. Now the question is 0.922 close enough to positive 1 to suggest that a positive linear relationship exists? In other words, does this mean that we have strong enough evidence to say that a linear correlation appears to exist? Well, we're going to have to put this correlation coefficient to the test. And so one of the ways that we can do that is we can go back to our number line, like I showed you before, and we can say, okay, if we're close to positive 1, that would be strong evidence for a positive linear relationship. If we're close to negative 1, that's strong evidence for a negative linear relationship. Well, how close do you have to be to positive 1, and how close do you have to be to negative 1? Well, we can find some critical values. Now, if we're going to find some critical values, this is going to be very much like hypothesis testing. Okay, so if we were going to make some hypotheses here, when you do a correlation analysis, your alternative hypothesis is always that the correlation coefficient for the population is not equal to 0. The null hypothesis is always that the correlation coefficient is equal to 0. And so you're assuming the null hypothesis is true, that the correlation coefficient is 0. If the sample correlation coefficient is far away from that, then you can reject that null hypothesis and come to the conclusion that a linear relationship appears to exist, either positive or negative, depending on which side of the spectrum you're on. Now, just like when we did hypothesis testing in the last chapter, we're going to need to work with a level of significance, an alpha value. In this case, let's work with alpha equal to 0.05. So In other words, if we come to the conclusion that we're going to reject the null hypothesis, we're willing to take a 5% chance of being wrong. That's what the level of significance really means. So the evidence has to be strong enough that the chance that we would reject the null hypothesis by mistake would be less than 5%. Okay, so how do we get the critical values? Well, the critical values for this kind of correlation analysis can be found in this table. It's called critical values for the PPMC. This table is not in the formula card, but it is in the back of the book. And this table is pretty easy to use. You've got the degrees of freedom listed here. Now for correlation analysis, pay attention. The degrees of freedom is n-2. Okay, remember when we did confidence intervals and hypothesis testing for the population mean, the degrees of freedom was n-1. Well, for correlation coefficients, it's n-2. Okay, you can think correlation involves two variables, degrees of freedom n-2. So in this case, our sample size was 6. 6 minus 2 would be 4. So the degrees of freedom is 4. And we're working with the alpha value of 5%. So we can just get the critical value 0.811. Okay, if we were working with 1% alpha, we would just use the other column. But 0.811 in this case is our critical value. So I mark that shaded region close to +1 with the critical value 0.811. On the negative side, you can put negative 0.811. And then you just see if your correlation coefficient is in the shaded region or not. In this case, 0.922 is in the shaded region. So that means that this evidence is strong enough that we feel comfortable rejecting the null hypothesis and coming to the conclusion that there is, or that there appears to be, a positive linear relationship. The evidence is strong enough that we feel comfortable saying that, because based on this sample correlation coefficient, we know the probability of rejecting that null hypothesis by mistake is 0. So conclusion, a positive linear relationship appears to exist. Again, I say appears because there is a chance, we know it's less than 5%, but there's still a chance that we're making a mistake. There's a chance that there really is no linear relationship here, and we just happen to get some data in our sample that made it look like there is. Okay, if I go back to the scatter plot for just a second, maybe if we had more people from the population, what we would see is that their dots are just all over the place like this, and there's really no pattern whatsoever. But maybe when we pick the 6 people from the sample, we just picked 6 people that made it look like there's a straight line pattern when there really isn't. Okay, but that's a risk that you always take when you do inferential statistics. But based on the sample, based on what we see, we feel comfortable saying that a linear relationship appears to exist. So if a linear relationship appears to exist, the next question that we'll ask is, what is the equation of the line that best captures that relationship? Okay, so in other words, if you wanted to draw the line on the scatter plot that does the best job possible of capturing the straight line pattern, what would the equation of that line be? Well, regression is an analysis that you can do that will tell you what the equation of that line is. Now, you might remember the equation of a straight line from your algebra class, y equals mx plus b. M is the slope, b is the y-intercept. In statistics, when we do a regression analysis, we call the equation of a straight line y prime equals a plus bx. So in the algebra equation, the number in front of x is the slope. So that means it's actually b in the regression line version of the equation, that is the slope. The number that's being added on is the y-intercept. So in the algebra equation, that was the b, but in the regression equation, that's a. Okay, so just be aware that a plus bx, a is the y-intercept, b is the slope. Y prime, the prime here just means that this would be a predicted value for y, as opposed to y, which is actually one of the observed values in the study. So one of the things we can do with the regression line that you'll see in just a little bit is you can use it to make predictions about the variable y if you know the value for the variable x. And so the prime just indicates that this would be a predicted value, not an actual observed value in a person. Okay, so here are the equations for A and B. And these equations have a lot of summations similar to the correlation coefficient equation. And even though it looks like there's a lot here, most of this work has already been done. We've already got all the totals, okay, and we've actually done even more than that, as you'll see in just a second. Okay, let's look at the equation for A first. If you were to go back to the chart of data with all the totals, you could just plug in the total of y, which is 433. You could go back and plug in the total for x squared, 79, minus the total for x was 19, and the total for xy was 1476. Now look at the denominator here. That expression is the exact same expression that was in the denominator in the first set of brackets in the correlation coefficient formula. So if you remember our correlation coefficient formula, that was the expression that was right here in the first set of brackets. And when we work this out, remember that number 113? I told you to highlight that step because we would want to come back to it. Well, we can just take that 113 because we know that's how the calculation works out. So I go ahead and I put in the 113, and then I can simplify down. Do the multiplies first. 433 times 79 is 34,207. Minus, and then 19 times 1476 is 28,044, and then divide by that 113. Okay, you can subtract and get 6163 divided by 113, and that gives you 54.540. That would be your y-intercept. Now, if you look at the equation for B, which is the slope, the numerator here is the same as the numerator in that correlation coefficient formula. Okay, so notice it's the same as the numerator here. So again, when we worked out the numerator, we got 629. So I can just take that 629 and make that my numerator in the slope equation. And the denominator, that's the same denominator that we had in the equation for A. You can see that they're the same. So it's going to be that same 113. So you just take 629 divided by 113, and that gives you 5.566. So our regression line, which is y prime equals a plus bx, would be 54.54, 0 plus 5.566 times x. So now you can use that equation to make predictions. For example, if you wanted to predict the final exam score for someone who studies 4 hours, just plug in 4 for x, and then you can simplify down. And if you simplify properly, you would get 76.804. Now, if you're going to make predictions, you should only make predictions for values of x that are within the range of values that you observed. So we observed values of x in this study that were between 1 and 6. So we should really only make predictions for people who study between 1 and 6 hours. We don't know if this linear relationship holds true outside of that range. So we shouldn't use the regression line to make predictions for values of x outside of that range. Okay, now a couple other things to mention here. Number one, if a correlation does not exist, so if you come to the conclusion that a linear relationship does not exist, there's no point in doing a regression analysis. There's no point in coming up with the equation of a straight line that describes a pattern that doesn't even exist. Okay? I mean, you could crunch the numbers and come up with an equation, but it's not going to tell you anything meaningful. So if there's no correlation, then there's no point in doing the regression. In those cases, if you had to make a prediction, just the average value of y would be the value that you would use to predict, that you would use for your prediction of y, no matter what the value of x is. Okay, that's the best you can do in the case when there's no correlation. It's just use the average value of y for all your predictions. Also, if there is a correlation, and that means a relationship exists between two variables, don't make the mistake of thinking that one variable causes the other. Okay, just because we know a relationship exists doesn't mean that it's a cause and effect relationship. Okay, so for example, you might have some paired data that says as the temperatures increase, there's more car accidents. You might find a linear relationship, a positive linear relationship there. That doesn't mean that higher temperatures cause more car accidents. Okay, there's probably other factors involved. When there's higher temperatures, more people want to go out, so there's more cars on the road, so there's more accidents for that reason. Or maybe when the temperatures are higher, people are uncomfortable, and so they get cranky and they drive aggressively, and there's more accidents for that reason. So it's not that the temperature causes the accidents, so we don't want to say that, but we can say that, well, there is a relationship, we just don't know exactly what the nature of that relationship is. So just be careful when there's a correlation that you don't take your conclusion too far and call it a cause and effect relationship. We can't determine cause and effect through correlation, only that there is a relationship between the two variables. Okay, well, that's correlation and regression, and that is what we need to know from chapter 10.